So good morning students. This presentation we are going to see finite state machine examples. Finite state machine is nothing but it has a present state, next state, inputs and output. It consists of two machines, Mealy machine and the Moore machine. Moore machine is nothing but it has a present state, it has a state with outputs the outputs and state change depending upon the inputs. The Mealy machine is nothing but it has a present state, next state, the next state and the outputs depending upon inputs and the present states. So this is about Moore and Mealy machine. Now we have the example. The example is parity checker. Parity checker is nothing but the sequence of information. In the information, we are going to find whether it is a odd parity or even parity. So the sequences number of bits. If the number of bits consists of even number of ones, the even parity. If it has odd number of ones, odd parity. Okay, a string of bits has even parity if the number of ones in the string is even. String is nothing but information. So the design a circuit that accepts an infinite serial stream of bits and outputs a 0 if the parity, the score is even and outputs a 1 if odd. Even parity means the output is 0, odd parity means the output is 1. Okay, so this is general block diagram of parity checker. The input is bit stream. The example is given. Okay, the sequence of bits 0 0 1 1 1 0 1. So this is the sequence of input given to the bit stream. Input clock output. So the output 0 will deliver if the even parity, number of ones is even. Odd parity, if 1 means number of ones in odd numbers. Okay, this is the clock signal. The input whatever we have that can be represented in this one 0 0 low, high high high. So you have 1, then low 0. So the output will be delivered. This is two zeros. Okay, so it's a even parity here. If 1 comes, okay, so automatically odd parity means the output is 1. Till this the output will be 0. Okay, because it's even parity. Then you have this is even number of ones. Here the output is 0. This is odd parity, the output is 1. Okay, so this is the clock input output depending upon the bit stream. This is the problem statement. Now we are going to design a circuit for this parity checker. First, we are going to do the state diagram. So the state transition diagram is nothing but it consists of only two states. The state is even and odd. So this is based on the Moore machine. The state diagram is obtained. So transition on each cycle with each new input over exactly one arc. So this arc is nothing but it's for the each and every cycle. The output depending upon the state. If the input is 1, first the input is 0. Input 0 means first input. Automatically no number of ones. So the output is 0. It states that it's an even parity. If input is 1, after this output, if you apply input is 1, the sequence consists of even or odd number of ones, it is the odd parity, the output is 1. Similarly, if you give input is 1, or this one and this one, what will happen? It's a even parity, the output will be 0. Okay, so depending upon the sequence, we have to find it. Here first 0. So it's a even parity. If you give 1, if the input is 1, it is odd parity. If again 1 is given, even number of 1, even parity, the output is 0. If after 1, if I give 0, 1, 0. Okay, this is also odd parity, this is also odd parity. Okay, so the sequence of this will be 0 here 1, this is 0 1 0, 0 1 0. So automatically this is odd parity, output is 1. But if you look at this sequence, this is 0 1 1. So odd number of ones, it's a even parity, output is 0. Okay, so this is the state transition diagram for the given sequence. The next one, state transition table. State transition table consists of present state, next state, output and the input. Okay, now the present state is given. You look at the state diagram, how the transition table can be executed from the state transition diagram. First you take the even. Even, what is output? 0. What will be the input? 0. Where it will stay in the same place. So it is even next state. The next one, what is the present state? Even. What will be the output? 0. If I give input is 1, where it will go? It will go to the next one. Okay, so this is can be given in this place. Okay, so this one, where it will go, the next state is odd. Similarly, you take a odd state. If it is odd, the output is 1, the input is 0, it will retain the same place, this part. You take odd, if the input is given as a 1, output is 1, where it will go? It goes to the next state, that is this part. Okay, so this part is given in the first one. So now the state input output next state can be executed from the state transition table. Okay, here 0 means even state, 1 means odd state. So the number can be represented for the present state and the next state. If the present state is 0, depending upon the inputs, what will be the next state? 0. So the states can be represented by the bits. Now we can do the circuit diagram from this simple truth table. Okay, now you have a output is equal to, output is same as, if you see the table, output is same as present state. So that is written here. You take this column and this column, both are same. So we can write output is equal to present state. Then next state is equal to, next state is nothing but we have to find output and the input based on this, sorry, the next state can be written as depending upon the present state and the input. So based on present state and the input, the next state is going to be defined. Okay, 0 0 0 1 1 0 1 1. So based on this we can write. Okay, so present state exclusive or with the input, it will generate the next state. So this is the diagram. Output is equal to present state. Input and present state exclusive or will generate the next state. You will give the flip-flop. Okay, because the states are defined in the form of flip-flops. This is inputs, this is output. Okay, so this is one example how to design a parity checker by use of Moore machine. Thank you.